Every electronic journey begins with a single component. Today, that component is the diode, and I am going to show you its superpower with just an LED, a resistor, and a DC power source. I first place a 1N4007 diode to the breadboard. Notice the silver band on one end. That band marks the cathode, the negative side. The other end is the anode, the positive side. Next, I add an LED in series with the diode. And because an LED is greedy for current, I place a 330 ohm resistor in series to limit its current flow. Now, for the heart of our experiment, the power. I am using my linear bench power supply. Watch closely as I slowly turn the voltage knob from 0 up to exactly 5 volts. Now, I connect the power supply to the breadboard's power rail, but we want extra stability. So, I add a 100 microfarad 25 volt electrolytic capacitor directly across the power rail. Now, I take a red jumper wire. One end of this wire goes to the positive power rail of the breadboard, and the other end connects to the anode of the diode. Then, I am using a brown jumper wire by connecting one end to the negative power rail and the other side to the free end of 330 ohm resistor. The circuit is now a complete loop. The LED glows to life. Now, I am using a tweezer to simply flip the diode. The anode and cathode swap positions. This is reverse bias. Total darkness. The LED does not glow. Why? Because the diode's gate is now closed. It is blocking the current completely. This, my friends, is the magic of the diode. Forward bias allows and reverse bias blocks. A one-way street for electricity. Now, let's measure what the diode is actually doing with the help of a digital multimeter. First, we have to enter into the diode testing mode. Then, I connect the probes to the appropriate COM ports. Now, I connect the probes to my diode. Red probe to the anode and black probe to the cathode of the diode. The side with the silver band. Now, this is forward bias. On the screen of DMM, it shows the forward voltage drop of the diode. Means the diode is conducting. Now, watch what happens when I reverse the probes. Red probe to the silver marked cathode. The screen shows overload, means no current flows. The diode is blocking the current. Now, let's see the diode's one-way street on the oscilloscope. I place the diode on a fresh breadboard. Then I add a 1 kilo ohm resistor in series with the diode. This resistor protects the circuit and gives us a voltage to measure. Now, I connect a blue jumper wire from the resistor's free end to the ground rail. For easy probing, I insert two male header pins at the diode's anode and one at the diode's cathode. Now, here is a tool I really love. It's a small PCB with male header pins. All the pins are shorted together underneath. A blue wire comes out from one pin, and the other end of the blue wire also has a male header. This lets me connect all my grounds, the function generator ground and the oscilloscope probe's grounds, to a single clean point. I simply plug the blue wire from my ground rail into the breadboard's negative power rail. That rail is now my common ground for everything. I take the ground clip of the function generator and both oscilloscope channels, channel 1 and channel 2, and connect all of them to my custom ground rail. Now all these grounds are connected to the breadboard's negative rail. Now channel 1 of my oscilloscope goes to the diode's anode. That's the input. Channel 2 goes to diode's cathode. That's the output. And the function generator output also connects to the anode. On my function generator, I set the frequency to 50 Hz. Then I set the amplitude to 10 volts peak to peak. Finally, I press the channel output button to turn it on. Now look at the oscilloscope. The yellow trace is the input sine wave. The blue trace is the output after the diode. See how the blue trace only shows the positive half of the sine wave. The negative half is completely gone. That's the diode doing its job, only letting current flow in one direction. Let's take a closer look. I zoom in on one single half cycle. That's one pulse of current. Now I zoom out horizontally. You see the blue trace becomes a continuous pattern of pulses. That's because the diode is turning the AC sine wave into pulsating DC. Now I adjust the trigger point up to the very top of a pulse. Peak voltage is about 4.2 volts. Now for a precise measurement, I use the cursor mode. I change the cursor from horizontal to vertical. Then I move the AY cursor to the peak of the yellow trace, the input sine wave. The scope reads about 4.8 volts. Then I move the BY cursor to the peak of the blue trace, the diode's output. It reads about 4.2 volts. That means the diode dropped about 0.6 volts. For a 10 volt peak to peak signal, the positive peak should be 5 volts. We measure 4.8 volts on channel 1. So we lost only 0.2 volts due to small resistance in the wires. That means the diode dropped about 0.6 volts. Our multimeter also measured 0.518 volts. It's so close. So let's recap. We built a simple circuit with a diode, LED and resistor. We saw the LED glow in forward bias and stay dark in reverse bias. We measured the forward voltage drop with our multimeter, about 0.6 volts. And finally, we watched the oscilloscope turn a full sine wave into only its positive halves. 3 different tools, one simple truth. The diode is a one-way street for electricity. This is Intellect Tronism. Keep building, keep learning. Thank you guys for watching this video. Please like, comment, share and subscribe. And don't forget to hit the bell icon for notifications. Stay creative and I will see you in next video.